All right, so good day to everyone. Although there's no one in the meeting, but we cannot wait any longer. So this meeting was supposed to start at around 6 p.m. So I waited for a complete hour, but unfortunately we do not have any people joining us. So I'll just start and record for myself. So anyone who wants to refer to these videos might just take a look at the YouTube channel. The YouTube channel, I'll share the details in due course. And you could also find them in the course page, the NPTEL course page. So my name is Shivang, and I'm a research scholar at IIT Delhi. I finished my undergraduate studies from IIT Delhi in 2020, and now, as part of my PMRF, that is the Prime Minister's Research Fellowships program, I need to take some live sessions for certain NPTEL courses. So here the session that I'm taking right now is one of them. So let's start. So effectively, we will be solving some problems that were actually, discussed in the CH20 course. So, so let's start. I'll be sharing my screen and you could just see the types of problems that we will be discussing. So just give me a moment. What we could do is that we could directly, maybe for lecture notes, we could just use the OneNote program. All right, so this looks perfect. Let me share my screen right away. And it's really unfortunate, but I cannot take off this mask due to the place I'm sitting at. So that does not allow. I'm a bit sick due to cold and all. So maybe the next time I'll be able to do a proper face reveal. Uh, yeah. Okay, so I guess everyone can see my screen right now. Let's just let us just delete this crap. Yeah. This is perfect. So how should we name this? Maybe problem solving session. Let's simply call it live session 1. Technically 1 or 2 does not matter, but still that would give it some kind of gradation to just include it as one of the videos of the playlist that we'll be creating on the YouTube channel. Now, okay, so the types of questions that we'll be taking up today will be basically based on week 3 content. So what does the week 3 content entail? It entails several video lectures and mostly on material balances. One of the topics that are that's covered in those videos is material balances. Some part of it is also incorporating some chemical reactions. And yet another part is talking about energy balances. So of course you could refer to the CH20 mass, momentum, energy balances in engineering analysis. Excuse me. Excuse me. That's the course name, and you can find it in the NPTEL platform. You can find it on the NPTEL platform. Anyway, so the key question here is we'll be taking up all these aspects of balances, different types of balances, and we'll be solving some problems related to them. So all this content is like really easy, but it sometimes makes people feel scared for no reason at all because there are really cumbersome equations that are provided to you, and you've got to use the mole concept to calculate what amounts of different reactants and products are being formed or are being left out, or how much of the reaction is proceeding in one particular situation or scenario. So without further ado, let us start our first question of the day. Okay, so maybe we could just start from here. Yes, so yeah, so I should probably also write my own name. Uh, I'm Shivang Rampriyan from IIT Delhi. Yeah, I think that's sufficient. That is sufficient, yes. So, okay, so we'll be taking up some problems, so let me check which one should I take for real quick. This is gonna be real quick. All right, so first question that we could pick up is, assume there's a lot of sour natural gas. So sour natural gas is basically natural gas plus hydrogen sulfide. So this hydrogen sulfide, it gives it a rotten smell. You know, it smells like rotten eggs. So, okay, so let me close my video for a moment because there are some bandwidth issues. Okay. Okay, so I hope everyone can see my screen. Okay, so somehow we need to remove this hydrogen sulfide that is present inside the natural gas. And as how to do that, we are actually using sulfur dioxide in its pure form, the molecule form without any contamination. We are using sulfur dioxide, and sulfur dioxide actually reacts with this hydrogen sulfide gas to yield solid state sulfur. That is the sulfur powder or layer or cakes, and it also gives you water in the vapor form. So remember, it's not in the liquid form. So that might be one point of confusion that people might have. Okay, so okay, so the first thing that we need to do is to write the reaction. Okay. Now the reaction can be written as let's write it as H2S plus SO2, that is sulfur dioxide, yields sulfur and H2O. We've taken some distance from the symbols so that whenever you want to insert some numbers, you could easily do so without congesting the entire equation. So first, let us balance it. So how to actually effectively balance everything is quite simple in the sense that you check out the element you check out the element that has the least number of occurrences throughout this equation. So, for example, sulfur is occurring in three places right here, but this is a free-form sulfur. That implies that whatever number you are inserting here, it does not matter. So it effectively all of the sulfur that matters in our balancing paradigm is coming from the reactant side. So we won't be and the reactant side is having two instances of sulfur. So we won't be touching sulfur for the moment. Now let's go to the product side. And in the product side, we see that uh, we've got two atoms of hydrogen and two atoms of hydrogen on the reactant side. But there is a single atom of oxygen on the product side, and there are two atoms of oxygen on the reactant side. So what we can conveniently do is that we use the two heres to make it balanced on both sides. Now, what's happening here, there are four hydrogen atoms right here, there are two hydrogen atoms right here, so we need an extra two here to make the total number of hydrogen atoms on the reactant side as 4. Now 4 is equal to 4, and the O part is still balanced. So now we have 2 sulfur plus 1 sulfur here, so that's 3 sulfur atoms. And since this was a free index, we can just insert 3 right here. So effectively now what's happening that this entire equation is balanced in the terms of elements. So we've got sulfur balanced, we've got oxygen balanced, we've got hydrogen balanced. So 2 is 2, and here's 2. We've got 4 hydrogen here, and 2 plus 1, 3 sulfur atoms here. And right away, and on the right side, the product side, you've also again got 3 sulfur atoms. Uh, so now what we could do is uh, okay, so let me take out some data, about what's happening inside the system. So let's crunch out. So let me think about some numbers that I could provide you, so that you could easily, find out some good solutions to this problem. Now, excuse me, please. Okay, so this is in the solid state. This is in the gaseous state. And this is also in the gaseous state, and this is obviously in the gaseous state. Now we know, let's say we know that we are getting around 5,000 kilograms of sulfur, or maybe for the ease of calculation, let's just say, or let's just take it as we've got uh, 3,200 kilograms of sulfur. So this is effectively, 3.2 metric tons of sulfur. 1 metric ton is 1,000 kilograms. Okay. So now we've got 3.2 metric tons of sulfur. So the first thing that you need to do in a chemical reaction, whenever some data or some quantities are being provided to you, you just need to convert everything into moles. And remember, there are really complicated equations, really complicated formulae, which, take different numbers and multiply them, take these two stoichiometric coefficients and take them and multiply them with the total amount of the substance and then divide it. And such a tedious mathematics is observable in most books and formulae, but you don't need to do anything at all. You just need to, feel the mole. So that is the key. You need to internalize how the mole concept is being implemented in a particular chemical reaction. That's all. That's all you need to do. So 3,200 kilograms of sulfur implies that you have around 100 kilomole of sulfur, because you've got 3,200 divided by 32 kg per kilomoles. This is kg, right? Okay, so this becomes 100. Fine. So we've got 100 moles of solid sulfur. This effectively implies that since we are assuming that we did not have any water vapor in the initial reactant mixture, we can precisely say that through simple unitary method or basic mathematics, we can say that the amount of water vapor, H2O gaseous, will be equal to 100 over 3 cross 2. That becomes 200 over 3 kilomoles. Now, as I told you earlier, that all of this stuff needs to be calculated in kilomoles. That is the best possible option you could ever have, because kg is not a consistent unit for chemical reactions. So everything's got its own molar mass, different molar masses. So the most uniform thing is the moles. So once you've got that, 200 over 3 kilomoles of water is being produced. Now, we are given that there are 100 okay. This implies that the exact amount of hydrogen sulfide that is being consumed and sulfur dioxide that is being consumed can be precisely calculated. This is because we have 100 kilomole here, 200 over 3 kilomoles here, and this, you see the stoichiometric coefficient here is 2, and here as well it is simply 2. So the number of moles consumed from the reactant side of hydrogen sulfide would be identical to the number of moles of water that is being produced. And just check this out, that the coefficient here is 3. Well, it is 1 here. So basically, for every 1 mole of sulfur dioxide being consumed, you are getting 3 moles of solid sulfur. Now, just go in reverse, that for every 3 moles of solid sulfur being obtained, you are consuming a single mole of sulfur dioxide. So for every 100 kilomoles of solid sulfur being obtained, you must consume 100 over 3 kilomoles of sulfur dioxide. Okay, so now we've got the consumption amounts, and let's call these X H2S maybe. So X SO2, and let's call the amount of sulfur produced as XS, and this is XH2. It's obviously not excess, as in more than required, but S, that is X and S, yeah. So, okay, so all of these are basically known. Now it is also given to us that the final mixture, let's say the final mix. So what's happening here, there is a certain, let's say reaction chamber. You've got H2S here, you've got SO2 here, both are reacting inside. Something happens, and you're getting 2 products out of this. One is solid sulfur, another is water vapor in its gaseous form, and there might be unreacted gases. Unreacted H2S and unreacted SO2 in the final product mix, and that might just pass unreacted from here because it's already exceeded the amount as dictated by the stoichiometric equation. So once this is done, we have the idea that so the product is entirely this. Product is entirely. This is the product. So we are given that in the product, the amount of H2O divided by the amount of H2S is given as 10. So okay, so this is XH2S, and originally this is XSO2, and let's call this X hash H2S. Let's call this X hash sulfur dioxide, and this is anyway simply X. Let's call this X hash as well. X hash S and X hash H2O. So a hash denotes the composition in the product. So XT, that is total of H2S, would be equal to XH2S. Now we are given that X hash H2O divided by X hash H2S is given as 10. So this implies that X hash H2S is equal to X hash H2O divided by 10. But X hash H2O is something that we've already calculated. And X hash H2O is basically like this, 200 over 3. This becomes 20 over 3 kilomoles. Now, X H2S is equal to the X reacted H2S plus X hash H2S. And we also know the stoichiometric amount of hydrogen sulfide that must be required to produce exactly 200 over 3 kilomoles of water vapor as a gas and 100 kilomoles of solid sulfur. And that amount that needs to be consumed is basically 200 over 3. That's kilomole. And we've already calculated X hash as 20 over 3 kilomoles. Adding both, you've got 220 over 3 kilomoles. That is roughly equal to, if you use a calculator real quick, 73.33 kilomoles. Similarly, XSO2 is equal to X reaction SO2 plus X hash SO2. And we are also given that in the final mixture, the final product mix, we've got XSO2 divided by XH2S is given as 3. There's this hash because it's talking about the product. Now, X hash H2S has already been calculated as 20 over 3. So X hash SO2 is identically 20 kilomoles. Once X hash SO2 has been obtained, and given we already know X reaction SO2, which is 100 over 3, so we can just add them both. 100 over 3 plus 20. This becomes 160 over 3 kilomoles, which is almost 160 over 3, 53.33 kilomoles. All right, so this is the total number of SO2 moles. And above, we've already obtained the total number of H2S moles. Okay, so once that is done, we are now, now the key question again comes that once you've obtained the number of SO2 moles and the number of H2S moles, we need to find the limiting reactant, the reactant that limits the reaction from proceeding to a completion. That is the exhaustion of all the reactants. So how to calculate that, we know that there are 2 moles of H2S are being consumed for every mole of sulfur dioxide. So this implies that if there are 73.33 kilomoles of H2S, then this would require something like 110 over 3, approximately 36 point, let's say 665 something. Let's say 36.7 kilomoles of SO2. But we've got 53.33 kilomoles, so that effectively implies that we've got more sulfur dioxide than is required, as calculated according to the stoichiometric ratios. So this implies that the limiting reactant is H2S, and the excess reactant is SO2. Okay, so I guess further you could also calculate the selectivity and or something like uh, extent of reaction, how much has the reaction proceeded. So you could, or you could also get the yield of the reaction. So you could all just look at these definitions and implement them in this particular problem. But what I have done is that I have told you the fundamentals of solving such types of problems. So you could easily extend these fundamentals to different types of situations and implement them in different scenarios to get your results. Okay, so there is another problem that we could discuss really, and this is a really good problem. So a bit confusing, but it's a good learn. It will probably serve as a good learning experience. So let's see. Let's take another pen. Where's the pen? Yeah, this is the pen. Okay, so let's draw a line here. Okay, so this problem is based on the hydrocracking. So, high carbon hydrocarbons. Excuse me, please. All right, so what is being done in this particular situation? What does hydrocracking mean? It effectively means breaking down a longer aliphatic chain of carbon compounds like this into smaller pieces like this. Well, this is just a representative example, so this might or might not happen. So let's assume a reaction chamber right over here. And you've got this hydrogen entering. Okay, so this is reacted with hydrogen in presence of some catalyst. This is a common, organic chemistry reaction. So, and you've got octane. Octane is basically an 8-carbon straight aliphatic chain alkanes. So carbons, basically, that's octane. And what this will yield is propane, butane, and pentane. Okay, and in the product, these products are found, this composition of the product is found as 19.5 is to 59.4 is to 21.1. So you know this all adds up to 100. So there's one thing that I would like to emphasize right over here is that why in chemistry we are mostly talking about moles, especially in the cases of gases, and why are these compositions provided not per mass but per moles. So these are all molar fractions. So effectively, it's not that they are being provided to you as moles for an easy solution of the problem. What's actually happening is that you might have heard about the laws of partial pressures. Typically, in all simple problems in chemistry, we are just taking every gas to be an ideal gas. And in an ideal gas, follow the law of the partial pressures. In that case, the partial pressure will depend on the number of moles of that particular gas in a certain gas in a certain gaseous mixture. So the partial pressure of that particular gas in the entire gaseous mixture is dictated by the number of moles. So effectively, when you're measuring gases, you cannot measure their masses individually because they're all mixed. They're all one homogeneous. They all form one homogeneous mixture. So you cannot separate them unless you are really ready to liquefy, but that is just stupidity. So what you do, however, you can measure their individual pressures, their partial pressures, and that gives you an idea of the number of moles. So effectively, what we are talking about might be actually the partial pressures of each of these gas components, but that is identical to, the number of moles, so the mole fraction of each of these gases or products. So that's why we are using moles as the representative concept for our calculations. Okay, so now this ratio is given. Now the problem here is that uh, let's take a representative reaction right here, and I'll illustrate to you what are the problems in writing this simple balance equation. C3H8 plus C4H10, C5H12. Well, if you want, then you could readily balance these all components with some numbers. Let's say if you work really hard, then you'll be able to get something like here comes 45, here comes 49, here comes 40, here comes 30, and here comes 24. However, the problem here is that these are free of the products that you are getting. There might be certain other products as well that you are not getting, that you are not, that are not visible in this particular problem. Side products or some leakages or some other problems. So that is why we must have an idea of the composition of the product streams, and that is directly used for stoichiometric calculations instead of balancing each and every element, because you do not know what other reactions or what other products might have been involved in the chemical reaction. But excuse me. But what we know is that all the carbon that is coming in these compounds is being obtained from this octane. So effectively, if we know the amount of carbon, the amount of total carbon in the entire mixture, then we might be able to do something with the amount of octane that was being used. And of course, some of it might have been left out. So let's balance carbon first. So this is element-wise balance because we know that the source of all the carbon on the product side is this octane gas on the reactant side. Okay, so let's call this the number of moles of octane that are being, let's say, reacted. Okay. Oh, so I guess someone just joined. Hello? Oh, hello. Good day to you, sir. DC, are you in the meeting? Anyway, so a bit of disturbance right there. So the number of moles of octane that have reacted in this particular reaction is given as, you know, you could just write it as you're given that there are so let us for an instance, let us assume that the total number of moles of product gases is 100. So out of 100 moles, you've got 19.5 moles of propane, 59.4 moles of butane, and 21.1 moles of pentane. So the total number of carbon, the number of moles of carbon. So what are moles? Effectively, moles, one mole contains Na, that is the Avogadro number. Uh, so this contains Na constituents. That the constituents could be anything. So it could be atoms, it could be molecules, it could be apples, it could be oranges. So effectively, one mole contains Na number of constituents. And now that we've got, so effectively, the number of atoms of carbon that are reacting should be equal to the number of atoms of carbon that are being produced, assuming 100% reaction rate, of course. So that is why we have put this, that is why we put this R right here, in that we are getting to know the number of octane moles that are being reacted right here. So this is only the reaction consumption part. So there might be some excess of octane that is being supplied in the reaction, which is typically the case. So there will be some amount of octane that is being left out. Now let's conserve the amount of carbon, the carbon as the element. So we multiply here 3 by 19.5, that is the number of moles of propane, plus we multiply, because, 1 mole of propane will be containing 3 moles of carbon. 1 mole of butane would be containing 4 moles of carbon, and 1 mole of pentane would be containing 5 moles of carbon. 4 cross 59.4 plus 5 cross 21.1. Anyway, so if you just do a quick calculation right over here, this, let's say it's got some value, let's say, or something value. And this, the total number of uh, moles of octane should be multiplied with 8, because the reactant side, for each mole of octane, you will be getting 8 moles of carbon. So that is why we've got this extra 8 right over here. And you just multiply, I'm doing a quick calculation on my calculator so that I can write the answer directly. 21.1 cross 5 is equal to something. Let's write it as straight away. Let's write it straight away as a fraction. And so in reactant of octane is equal to divided by 8. This is 50.2. Let's say we're talking about moles, so we talk in moles. Okay. Now this is the amount of octane that has been consumed in this particular reaction. Now, we are also given that all the hydrogen that is being produced on the product side is coming from the reactant side. So that effectively implies that 18 times, if we again apply a conservation of the element or the atoms on both sides, then that effectively implies that 18 times NR of octane. So each molecule of octane would be yielding 18 atoms of hydrogen, and that implies that each mole of octane would be yielding 18 moles of hydrogen atoms. So this is the balance. Plus, let's assume some coefficient of hydrogen gas, the isolated hydrogen gas as X, and let's call this NH2. Reactant, of course, we don't care about what's being left out at the moment. And that is equal to 8 times 19.5, because again, 1 mole of propane would be yielding 8 moles of hydrogen atoms, and 1 mole of butane would be yielding 10 moles of hydrogen atoms. So that becomes 59.4. And again, for each mole of pentane, you'd be getting 12 moles of hydrogen atoms. So just multiply by 12, and it becomes 21.1. Now, solving it further, you could just give me a moment, and I'll be solving it on my calculator screen. So this becomes 59.4 plus 12 cross 21.1. Well, you could also solve it orally, to be really honest. It's not a hard calculation, but we don't need to waste all that time. Okay, but we already know that the number of moles of octane that have reacted or have been consumed in this particular reaction is 50.2 plus X times NH2 and R. Okay, so this X, I have just basically put it. So, every mole of hydrogen gas gives 2 atoms of hydrogen. So we just write 2 here. So there is a single variable here. There is a single variable here. This can readily be solved using simple addition and subtraction from both the sides. So this becomes NRH2 is equal to 1003.2 minus 18 so let's say 6.3, 8 and 5 and 19, answer 3 over 0.6 divided by 2. So you just write it as 1003.2 minus 18 cross 50.2 equals to something, and divide this by entire self by 2, so this becomes 49.8. Oh, we just forgot to write the sweet mole. Okay, so now we've got the amount of octane that is reacting and the amount of hydrogen that is reacting on both sides. And after this, we could further have we could play with this a little bit, like calculating something like selectivity, how much amount of reactant or product might be left out or something, similar things. So that is all an extension of this problem. But I know that I seriously really hope that once you've gone through this particular problem, you should be able to solve all types of problems uh, based on this particular question. So whatever the extensions are, you just need to know how those terms are being defined, and you're good to go. Anyway, I would like to take another problem, to be really honest. But we don't really have much of a time. Oh yeah, so this one is a good question actually. Let's pick this up. Or you might just